This is lecture number I think it's the 10th in the unit number 2, lecture number 2. Okay, so write it as a 10th lecture. Okay, so it belongs to the unit number 2. So better I write in this way. Okay, unit number 2, lecture number. Okay, so we have been discussing about the electrical characteristics. Electrical characteristics of MOS transistor. So that too exclusively we are talking about NMOS transistor. Okay. Fine. Now in the last class we have derived that. Okay. So let us recapitulate for 2 minutes. We have considered gate something like this. Okay, and there is a gate oxide on top of it. There is a polysilicon on top of it. Okay, so if I consider the 3-dimensional view, something like this, it will be happening. It will be shown something like this. Okay, so this is how it look like. So we have a source here, N plus. We have a drain here, N plus. So the distance between the source and drain is called as the length of the transistor. Okay. So the thickness of the oxide is one of the important parameter. So this is what the thickness of the oxide. It is decided by Tox. Or I can say that the distance between the metal one, so metal to substrate. Okay. So or I can say that the channel also. So I can simply say that the channel also. Channel I can write it in this particular magenta color. So this is the channel. Okay. So the distance between the metal and the channel can be called as oxide thickness also. Oxide thickness can be considered as channel thickness. Sorry, I'm extremely sorry. The distance between the metal and channel. Okay. Now, in the last class we have seen that the transit time tau. So the current we want to calculate, the current IDS, the source to drain current, is nothing but channel charge induced to the channel charge divided by transit time tau ST. Source to drain transit time. Okay, so we calculated tau ST as tau ST. That means the time taken by the carrier to move from source to drain. Okay, so how do we define then? How to define the transit time? The transit time is defined by L square divided by mu n into VDS. So it is L square divided by carrier of mobility of the electron and with VDS. Okay, so this is what we have calculated, we have derived in the last class, right? So this is what we have derived in the. So what we concluded then from this point of view, so the tau SD, the source to drain carrier transportation, the time taken by the carrier to move from source to drain is directly proportional to the to L square. Okay, if you are reducing the length of the transistor and drastically the time taken by the carrier to move from source to drain will be reduces, the delay of the time will be reduces, and that is the one, and it is inversely proportional to that of VDS. Okay, so if the electric force between the source and drain is high, then the time will be reduces. Okay, so our objective is that we have to reduce the time taken by the carrier to move from source to drain. That is the main objective. So in order to achieve that thing, we have to play with these kind of parameters. One is the device point of view length of the transistor and terminal point of view VDS. right? Now let us consider how do we calculate QC. So QC, how do we calculate? QC, it is nothing but what we can call it as channel induced charge. Okay, the amount of the charge that is induced in the channel that we have to calculate. So with this parameter and with the parameter the tau st, we can calculate how much amount of the current will flow within the device, right? Okay. Now the QSD. So how do we define the QSD then? So the fundamental equation for this Q is channel charge. So what is the charge that we are talking about? We are talking about the capacitive plate. So we have here we have source, one conducting plate. This is another conducting plate. These two conducting plates are separated by, for example, an oxide, for example. Okay. Oxide is covered here, for example. This is a capacitor. Okay. So how do we calculate the channel charge here? Sorry, I'm sorry. How do we calculate the induced charge on the other plate? For example, if you put a positive charge at this place, negative charge must be induced at this point, right? So how do we calculate this one? Okay, so the positive plus to negative, okay? So what this charge that we want to calculate? We want to calculate this charge. What should we do then? QC, our induced charge, is proportional to that of, according to this one, just wait 1 second. The channel charge is proportional to that of how much electric field that is existed between that. So that's what it can define. So the charge that is induced on the other plate will directly proportional to that of the electric field between these two plates. Clear? No. So let us apply this kind of thing. What kind of charge that we are talking about here? The charge of the channel. Okay, we want to talk about the channel charge. So the proportional to that of what is the electric field that we talk about? So as you can see here, the electric field is a horizontal, or sorry, vertical electric field is required. Okay, positive to the negative. So the positive charges we placed here, the negative charge is induced at the channel because of the carriers. Therefore, the electric field direction is from top plus to negative. Okay, so what is this electric field? We can call it as gate to channel electric field. That's what we should remember. It is nothing but gate to channel electric field is important. Not from source to drain, or sorry, not from drain to source electric field. It is the vertical electric field, something like this. Okay, so therefore, this electric field is called gate to channel electric field. Okay, now we can remove this proportionality constant, and the QC is equal to, since it is a medium, what is the medium that we have considered? The capacitive medium. That means permittivity of the medium is required. Okay, so therefore the permittivity means epsilon that we have to consider. So we have to remove the proportionality constant with respect to the epsilon because of this one. And with respect to this, EGC is required. Another important point is that this charge is only we have considered for the unit area. That means only the unit area we have considered, for example. If the entire area, if you want to consider, then what we have to do, so we have to consider, of course, this is the width of the channel. This is the width of the channel, okay? And this is the length of the channel. This is the length of the channel, okay? So therefore, we are talking about this entire space that we are talking about, okay? So for example, you consider a gate. So the entire width we have to consider, entire length we have to consider, okay? So that's what I'm writing here is the total area, W into L, total volume that we have to consider. That, sorry, it is actually the width, the area of the total area of the capacitor. Are you agree with me how we are getting the epsilon, how we are getting the ECC, how we are getting the W and L? Okay, now, so this QC can be defined by Of course, epsilon is actually permittivity of the medium. Permittivity of the medium is defined by permittivity of the free space into permittivity of the relative permittivity of the medium. Okay. So actually, the what is the oxide that we are considering here? Silicon dioxide. So for the silicon dioxide, relative permittivity will be defined by 4 times. It will be approximately 3.9 actually. We consider the 4. Also, we can consider. Okay. And epsilon naught, everybody knows that. Permittivity of the free space. What is the value? That is 8.854 into 10 to the power of minus 14 farad per centimeter. That's what we can write it. Of course, epsilon can be defined in this way. Now, it's a very important point is that how do we define EGC? Okay, so that means that the channel must be induced in the the carrier is induced in the channel. If the carrier is induced in the channel means we have to apply some potential at the gate. Okay, that means that as we can see that here, you see here, for example, here is a oxide, here is a polysilicon. If you want to induce a channel here, then when negative carriers is introduced here from the bulk, we have to apply a sufficient voltage at this point. Am I right? So that means VG that we need to apply. So how much VG we should apply so that the inversion charge is developed here? Whatever the potential that we apply here, that should be VGS minus of VTH. Okay. So gate to source voltage, which must be greater than that of the threshold voltage, then only the channel will be formed or inversion charges will be formed. Are you agree with me? Okay. So therefore, the potential difference between the gate to the channel, is responsible gate to the channel, or that means I can say that channel voltage, for example, I can say that. So this VGC will decide how much amount of the charge will be developed here. Okay, so that is relevant for this one. Okay, therefore I can simply say that what is the EG actually? E is actually in the last class we have seen. EGC, electric field between the gate to source, is nothing but the potential difference between these two plates. Okay, the potential difference, I can write it here, is the potential difference. The potential difference between the gate and channel divided by the distance between the plates. Distance between plates. And that's what we fundamentally we can define the electric field between these two plates. So what is the potential difference here? Now we need to consider the potential difference between a gate and channel. The potential difference between gate and channel. Gate and channel. Okay, so between the plates and now gate and channel now okay, what would maybe. Now the potential difference we can call it as VGC, right? Divided by the distance between the two plates. What do you mean by this one? The distance between the plate is nothing but Tox only. This is called Tox only. So therefore I can write it as Tox. Clear? Now what do we define this VGC here? The potential difference between gate to channel. What is the potential that is required at the gate? The potential at the gate is VGS minus of VTH, right? So this is the potential, or this is the voltage that we have to apply at the gate. Then only the magnetic arrays will be generated or inversion layer is formed under the silicon dioxide minus the other. So VGC is nothing but, V gate voltage minus of V channel voltage. That's what we normally write. So VG actually what I have written, VGS minus of VTH. What is the VC? So the voltage across the channel, is not uniform, as we have mentioned. As we keep on increasing the VDS value, Sometimes it is something like this. Suppose, for example, so this is the channel. Okay, this is the channel, for example. So sometimes the channel is something like this for a particular voltage of, uh, yeah, the channel is something uniform channel will be there. After some time, when the VDS is changes to some value, it will be going in this direction also. So if you use another supply voltage, for example, then it will come to this point. So it will be going something like this. That means uh, you can observe that there is a uniform channel is observed between these two, but the channel is available at this point now. The channel is at this point now. That means that by applying the VDS value, okay, as we have seen previously, or otherwise I can write it clearly in this way. So the channel is something like this. By applying the VDS value, the channel will be shrinking towards the source side. Okay. So that means that the charge available in the channel is not uniform. Okay. So that will be depending upon the VDS value, how much that we are applying. So for the time being, just assume that there is a uniform channel is existed. Assume that there is a uniform channel is existed, something like this, the uniform channel. Okay. So in this assumption, under this assumption, the voltage across uniform channel is existed, something like this. Okay. Under this condition, the voltage across this channel will be VDS divided by 2. Let us consider in this way. Ante kada. Ikkada manaki drain undi ikkada n plus source. We have n plus drain. Okay. So the potential between the voltage drop between this channel is nothing but VDS only. Ante kada. This is actually VDS only. So the voltage across this channel is nothing but VDS only. But what we are assuming that, so it is a fair approximation is that we take the average value existed between these two. Instead of VDS value, I can consider VDS divided by 2. Okay, so therefore, because the channel is all the time, it is changing from this point to this point and this point and this point, something like this. Okay, therefore, better you can consider that the average value is the best choice for us. Okay, so in that sense, I'll write VGS. What is the gate VC here actually? VDS divided by 2. Right? So divided by, what is the distance between this one? As I mentioned that it is a TOX only. It is a TOX. So this is what EGC. I hope you understood how we have derived the VGC value. Okay. Now, so come to this point and we'll discuss that one. Okay, put it here, and I want to write VGC as VGS minus of VDH. It is a sufficient voltage over VDS divided by VD2 at the channel divided by TOX into W into L. Okay. So this is the equation that we can derive for the channel charge. So everything is possible now here. So this is the fifth equation. Equation number 5. Okay. Now substitute. This is actually in the previous class. It is mentioned that this is the fourth equation. Okay. Substitute 4 and 5 in original equation, in the basic equation. Substitute. Equation number 4, comma 5 in equation number 1. So equation number 1 and what is the equation number 1? IDS value is equal to QC divided by tau SD. So what is the QC here now? So we can substitute that one. So QC is nothing but epsilon naught into epsilon r into VGS minus of VDH minus of VDS divided by 2 into W into L divided by Tox, I can write it here, is multiplied with L square divided by n into VDS, right? Just only I have substituted the equation 4 and 5 in equation number 1. So this is actually the equation number 1. Okay. So let us rearrange this equation in a meaningful fashion. Okay, L square will get cancelled, right? So L square and L will get cancelled. Okay. So this mu n into VDS will be going upwards. Okay, so I'll write it here is mu n into VDS into epsilon r into VGS minus of VTH minus of VDS divided by 2. Of course, better to move the, okay, let it be like that only. Don't move the VDS divided by 2 in other direction. Into W divided by L into Tox. Okay, that is how we can write. Just only mu n move to upwards. That's all. Nothing else in it. So now we can write it here is in a different manner. Epsilon and epsilon are the constant values. Put the constant values in one direction, one place. Divided by Tox divided by Tox into mu n is also there. Mu n into, these are all the constant values, right? Mu n, epsilon naught divided by Tox. Tox is also be treated as a constant only. Okay, for the time being. And W by L are the variable parameters. Okay, W here is we have a W, here we have a L. W by L into VGS minus of VTH minus of VDS divided by 2 is multiplied with VDS. So this VDS I put it that side. Okay, that's it. So therefore this is called IDS. Okay, so this is a very important equation for us. Okay, so this is how the current equation we have calculated. Okay, so this much amount of the current will flow within the MOS transistor, NMOS transistor. Okay, so let us rearrange this one in more meaningful manner, more meaningful structure. Okay, generally alternative ways we can write alternative ways to write IDS value. Okay. So here also we can understand that IDS value is equal to mu n, we can write it. This entire thing we can call it as Cox. The capacitance, the unit capacitance that can be seen at gate to channel, at gate to channel capacitance. So let us consider it in this way. Of course, I write here. So we have a oxide, we have a polysilicon, we have a source, we have a drain, N plus, N plus. So, okay, so what is the capacitance that we can see, the unit capacitance that we can see in this structure? Okay, the unit capacitance can be seen at this structure. Okay, so whatever the capacitance that we see here, this capacitance is called Cox capacitance. So what did the C actually say that capacitance, how do we define? Epsilon divided by distance D. Okay, so therefore the epsilon is actually the medium related thing. Okay, oxide, the distance between the places, Tox only. We are talking about the unit area. Unit area means only one we have to consider. Okay, so that's the reason why epsilon naught into epsilon naught by Tox we normally call it as Cox. Okay. Now this multiplied with W by L into VGS minus of VDH minus of VDS divided by 2. So whenever I ask this question, you should remember this one. VDS. Okay, so this is another alternative way that we have to consider. This equation you should not forget. Okay, it's a very important equation. Now we have to derive some. We have to conclude some point here. So let us write some notes here. Let us write some note. What is the relationship between the IDS and VDS in this situation? Okay, as you can see, IDS value considered. IDS value. IDS value is directly proportional to that of W by L ratio. There is a 1 point that we can remember. And IDS value is proportional to that of VDS also. So that is VGS minus of VDH minus VDS divided by 2 into VDS. Of course, remaining two things are actually the constants only. Okay, mu n into Cox is a constant value. Transconductance parameter. Okay. Now we can see IDS is the device point of view W by L ratio. It is depending upon IDS value is depending upon VGS minus of VDS, something like this. So generally, this is actually the linear relationship. So put it the IDS value in terms of the W by L ratio. If we keep aside, you consider this a second important thing. Here, IDS value is linear relationship with VDS. That's what very important point that we have to remember. IDS value is linearly related with VDS value. So do not forget about this. It's a linear relationship. Are you agree with me? Okay, so that is what the 1 point that we have to remember. So another point we have to remember here is from the basic point of this equation number 1, and that means W by L ratio. If you want to increase the more current, actually we need more current. Okay, whenever we are releasing the device, we need more current. If you want to achieve the more current, what should be the condition that we have to meet in device point of view? Anyone from the class? I want to increase the current value, IDS value, with respect to the W by L ratio. So with respect to the W, with respect to the L, how much values are suitable to increase the IDS value? Anyone from the class?
Sir, reduce length. Sir, reduce length, sir.
Yeah.
Or increase width.
Yeah, exactly. Thank you. So what we have to do? We have to either increase W or decrease length. These are the two options are there. Okay. So, but the people are not advisable to increase the W value because it leads to high input capacitance. High input capacitance. Okay. So therefore that leads to the delay of the circuit. Okay. So high input capacitance is not suitable actually. So therefore we are not interested to increase the W value. So therefore the people are trying to achieve the length. It is a suitable approach. It is a suitable approach. Are you agree with me? That's what we have. That is the reason why people are trying to reduce the length of the channel. That's the reason why they achieve the from 330 nanometer technology to 45, 65, 22, 32 nanometer technology they have achieved. So they have started from 320 nanometer, I think 320 nanometer to 180 to 220 and 180, 90, 65, 45, 32. Like this, the length of the transistor is reduces so and so. So after 32 onwards, FinFETs came into existence, but after up to 32 nanometer, they are able to achieve the length of the transistor as small as possible. So in order to increase the current value. Okay, that's it. So therefore, another point we have to remember here is that so what if is what if VDS value is equal to VCS minus a PTH? So that means that I have defined in this way. Okay, just a second, 1 second. Okay. So what if VDS value is equal to VCS minus PTH? Generally, what we have done is that if there is no, if the VDS value, for example, here you consider the VDS value, here we consider the IDS value. If the VDS value is less than VDH, no doubt there is no current flowing here. There is no doubt there is no current flowing here. The ID value is equal to 0. Okay. So whenever there is a VGS is more than that of the threshold voltage, then what will happen? So this value is going on increasing something. The linearly it is going in this way. Okay, so this is one for one particular VGS value. So this is one particular. So here is actually VGS value is less than VTH. The current value is something like this. Here VGS value is greater than that of the threshold voltage. So we consider this is VGS1, for example. So if you keep on increasing the VGS value, for example, if you keep on increasing the VGS value, more number of carriers are available. Okay. So this is how the linear relationship is a holds good. Because more carriers are there, it will be remains in the linear region. Okay. When IDS is linearly related with VDS means it is in the linear region. Okay. So therefore, there is a linear relationship is existed between VDS value and IDS value. So as VGS1 is greater than that, VGS2 is greater than that of VGS1. For example, it is VGS2. For example, when VGS2 is greater than VGS1, the mass transistor remains there in the linear region for more amount of the time. That's what we observe. Okay, fine. Let us increase further VGS value. Let us increase further VGS value. Then again, it will go from something like this. So all these three line waves are always says that it is a linear mode of operation. Now all are in the linear mode of operation, VGS3 for VGS3. So here we have to assume that VGS3 is greater than VGS2, which is greater than VGS1. Agreed? Now, so certain point where the point, for example, at this point, let us consider in this point. So at this point, when VDS value is reached to particular voltage, this particular voltage we normally call it as, for example, VGS minus a PTH. So this is the voltage of VDS that we are talking about. So at this VDS value is equal to VGS minus a PTH, the transistor will enter into the saturation region. The transistor is enter into the saturation region, as we have seen previously. What do you mean by a saturation? When it will enter into the saturation. So that means that if I keep on, if I use that VDS value is equal to VGS minus a PTH, something like this. If I substitute this into this equation, for example, note number 2 equation, for example, this equation, what will happen? The IDS value is equal to, I can say that this is the fundamental equation, right? For example, this is the sixth equation. Let us consider. This is the sixth equation. Let us put it in the sixth equation. Substitute equation number. For example, it is 7. Equation 7 in equation number 6. So what is this one? So mu n into Cox into W by L into VCS minus of PTH into VDS divided by 2 is multiplied with VDS. If you substitute the VDS in place of VDS by VCS minus VDS, what will happen? Mu n into Cox into W by L into VCS minus of PTH minus. So what the value that I can write it? VCS minus of PTH divided by 2. Okay. Is multiplied with VCS minus of PTH. If you multiply inside of this one, what will happen? Mu n into Cox into W by L into VCS minus of PTH whole square minus VGS minus of PTH whole square divided by 2. So this is actually the same parameters. Okay, so mu n into Cox into W by L into, it is actually VGS minus of PTH whole square divided by 2. 2 is multiplied here. 2 minus 1 divided by 2, something like this only. So this is what we have to identify. This is what we have to identify. Okay, so what we observe that in this case, what we observe, note, what we observe, let us consider one note here. So here the IDS value is only proportional to that of VCS minus of PTH whole square. Of course, by 2 is also there. So therefore, what I can say that by avoiding the channel length modulation concept, just by simple basic understanding, we are not considering the channel length modulation. Okay, so in this situation, IDS is independent IDS is independent VDS value. So in previously what we identified that, what we have assumed that the IDS value is linearly related with VDS, but it's independent. The independent relationship is there. That means what do you mean by the independent relationship? Means even if VDS values increases, IDS value cannot increase. That's what we have to understand. Because in this particular equation, there is no VDS actually. In this particular equation, you observe there is no VDS value. Okay, so therefore what we can observe that. So okay, what we can observe. So please give me for 2 minutes time. I will complete it. Okay, copy. Paste here. So what I can observe that there is a, even if you are increasing the VDS value from this point of view, it cannot change, right? So it remains same. So why actually the current has to go to zero actually, but it is not going to zero. Why? Because so there is a drift mechanism is existed near the drain side. That's what we clearly mentioned previously. So the carriers will attain the energy and drift towards the drain side. That's the reason why. So it is not going to zero, but it maintains constant. That means anyway, it is not at all increasing. That's what we remember that. So actually it is not increasing something like this, or it cannot decrease in something like this. So anyway, it is not increasing. It has to go decreasing. And it has to go to decrease, but it's not going to decrease. It will be remains constant because of the drift mechanism existed near the drain side. Similarly, the same thing is applicable for this one also. Similarly, the same concept is applicable for this one also. The same kind of thing is applicable for this one also. Clear? So this is how we can derive the mathematical equations for to characterize the mass transistor. So generally this is called saturation current equation. Saturation current equation. So this is called linear current equation. This is called linear current equation. Okay. So this is what the today's class, and remaining things we will see in the tomorrow's class or the next class. If you find any difficulty, please let me know. Okay. We stop here today. We will discuss the remaining things in the next class. Thank you. You can leave.